Hello everybody, I'm here with an example of what we call or what we know as dependent motion. These are problems involving pulleys that connects blocks together. I have shown you already some examples of this in other videos or during the Zoom lecture. But this problem is a little bit different. This problem looks very innocent in terms of the type of motion that we have, but actually as you come up with the governing equation that describes the motion or relation between position of A and B, you'll see that actually when you differentiate, it could be actually, it's not difficult, it's just that you have to be very careful with your differentiation. Anyway, so what is this problem? Here we have this kind of roller A confined to move horizontally to the left. And at this instant, what instant? At the instant when XA is 3 meters. So this XA shown here is 3 meters. Basically, we're going to use that as describing the position of roller A. We are told that velocity of A is 4 meters per second to the left. So A is moving obviously to the left, and it's accelerating at the rate of 2 meters per second squared. So at this particular instant, we want to find velocity of B and acceleration of B, acceleration and velocity of this block. So the way actually you start the setting up this problem is very simple. Always you have to come up with the total length of the rope and describe the total length of the rope in terms of the, these variable position vectors, the two particles in question, A and B. So already we have this guy described as XA. So let me redraw this for you. So remember, the position has to be from a non-moving reference, okay? So a fixed reference. And I'm going to call this guy from here, keeping track of position of B, and I'm going to call this Y of B, or I can call it X of B. It really doesn't matter. You can use anything you want. So now let's go ahead and find the total length of this rope. By total length of the rope, I mean this length here. So it is obvious that the total length of the rope here, L, as we call it, is Y of B, right? This portion, right? Plus, so the first thing comes to your mind, you say, oh, if this is 3, right? If this guy is 3, and I know this vertical distance is 4, so the length of the rope is 5. But remember, that length is not going to be 5. At this instant is 5. We want it in terms of the variable X of A. And Y of B. Okay, so what is that? That would be actually square root of, using the Pythagoras equation, X of A squared plus 4 squared. So in a way, L is equal to, if you put it in the form that would be more desirable in terms of the differentiation, which is what we're going to do in a minute. So we make that X A squared plus 16. Instead of radical, we put power 1/2. So this is basically the governing equation describing the relation between the position of A and B. So what we have to do now, we have to be careful from now. Remember, we're going to take the derivative of this equation, d dt of this equation. Let me actually use a different color here. All right, d dt of this relation. So let's go ahead and do that. So we want the derivative of a constant, which is going to be 0. Then we have the derivative of Y of B with respect to time. Remember, these are all time derivative. What about this guy? We have to use chain rule. So power comes down times whatever you have inside the radical, inside the parentheses, to 1 power less. 1/2 minus 1 is minus 1/2. And then we go inside and take care of the derivative of inside. So the derivative of 2XA squared becomes 2XA. But what you forget is that you're taking derivative with respect to time. So you have 2XA dt, and then the derivative of 16 is 0. Okay? So this is the part that always people make their mistake. Because you always in calculus, on the side here, guys, you say, okay, y equal x squared. What's the derivative of y with respect to x? You say, okay, no problem, it's 2x. But what's the derivative of dy, y with respect to time? It's actually 2x dx dt. Okay? So this is what I wanted to show you here on the side. And the reason for that, by the way, to just show you, dy dt actually is dy dx times dx dt. See, this is the dx dt here. You see how dx and dx cancel and you have dy dt, which is what you have here. So dy dx is the 2x, right? And then you have dx dt. All right, guys, I'm going to erase this so you don't get confused. So let me get rid of this guy here. You can obviously pause the video and write that down if you want to. But anyways, let's get back here. So see, dy, the derivative of y with respect to t is velocity of b, rate of change of position. And this one, we just rewrite it as it is. And I'm going to clean it up in a minute. Or not clean it up, actually, because I want to take another derivative in a minute. So basically, these 2 and 1/2 actually cancel, right? So I can get rid of this. So this 2 and 1/2 cancel, right? And then I have x of a here. Yes, use the regular color. And this becomes velocity of a, rate of change of a. So you can go ahead and actually say velocity of b now is negative of xa squared plus 16 to power negative 1/2 times xa times velocity of a. Or you can even write it if you want in this form, xa velocity of a, and then you could put this expression back in the denominator because it's a negative power, and back inside the radical if you like. It's all up to you. And don't forget the negative here. So if you go ahead and plug in the numbers, xa is 3 at this instant, velocity of a is 4. By the way, this is taken as positive here because that's the direction that this guy is defined. Okay, divided by 3 squared plus 16 squared, 16 rather, this becomes a 5 in the denominator, minus 12 over 5 becomes a negative 2.4. Why negative? Because that implies that velocity of b, see, this is the positive direction. So it is clear that v has to move up, opposite of what we have defined as positive, because obviously as a moves to the left, b has to move up. So here's your velocity of b at this instant. So what about acceleration? I got to move to the next page. So I have an expression for velocity of b. I just have to take the derivative of that and get the acceleration. So let's do that. Let's see. This is what I'm going to actually use. It's much easier to take the derivative. So I'll move to the next page, and I say velocity of b was what? Was minus x of a squared. Actually, let me put it in a better format. So I'll put minus, minus xa, velocity of a, times xa squared plus 16 to power 1/2. This is where you have to be extremely careful, guys. You have basically 3 terms here. And you have to use, as you take the derivative of this, which becomes acceleration of b, you have to take the derivative of this whole thing here. And keep in mind that you can factor the negative, of course, and you have to use a triple product rule, actually. Keep in mind that, again, that you're taking derivative with respect to time, okay? So let's start with derivative of the first. So derivative of the first times second times third, right? Plus first xa times the derivative of va, which is actually acceleration a, times third. I'm running out of space. Plus, I'll put the last term here, plus first second times the derivative of the third. What is the derivative of this guy? Again, 1/2 comes down, xa plus 16 to 1 power less, right? And then you go inside, take the derivative of inside, which means, again, the same story as chain rule. Close the bracket. And then, of course, derivative of 16 is 0. Okay, so just keep in mind that this is, again, velocity of A This is acceleration of A. This is again velocity of A. So you just have to go and clean this up a little bit. You don't have to clean it up and you can just plug in the numbers, but let me just clean it up for you a little bit. Acceleration of B becomes a negative of, let's see how we can clean this up. This becomes a VA squared. Let's see what term that could be combined. Plus XA, acceleration of A. These two have the same, you know, by the way, this was, I did make a mistake, guys. Sorry, I gotta go back and clean this up. You have to, I just apologize for this. This was -1/2, guys. Okay, no problem here. I'll make this a -1/2, -3/2. No big deal, guys. All right, no panic. This is the wonderful, you know, story of, you know, when you do things live and, you know, you don't want to, you know, edit it. Life goes on. All right, so that takes care of these first two terms, I believe. And then the last term, the 2 and 1/2 cancel, and then you end up getting an XA squared, looks like a negative XA squared VA squared. And this in the denominator actually becomes XA squared plus 16 to power 3 here. I believe this is the expression. And then if you go ahead and plug in for velocity of A, which is 4 meters per second, and acceleration of A, which was 2 meters per second squared, right? And position XA, which is 3, you have everything here. Go ahead and solve for acceleration of B. And I believe it comes out to be very close to negative 3.25 meters per second squared, right? Which again implies what? Acceleration of, remember this was a positive direction. Acceleration of B rather would be 3.25 meters per second squared in the same direction as the velocity. Okay, guys, so you see how the equation was so simple, or getting the relation between position of A and B was so simple, but when you differentiate it, you have to be very careful. You're taking the time derivative, you're taking derivative with respect to time, and you have to use chain rule. And then you notice that we had to use triple product rule here. So you have to really be a good bookkeeper in a way. Take the derivative of the first, multiplied by second, multiplied by third, then first times derivative of the second, as I showed you here, times third, and then first, second, times the derivative of the third. Okay, hopefully I haven't confused you. As always, would be appreciated if you subscribe to the channel, and just as I said, I would have videos coming up as needed. And thanks as always for watching and listening. Have a good day.